We continue our review of finite limits by looking at limits involving roots in the case of the indeterminate form of 0 over 0. So let's look at the following example. Let's say we have the limit as x approaches 0 of the square root of x squared plus 1 minus 1, everything over x squared. So when we try to evaluate this function at 0, what we get is the square root of 1, so 1 minus 1, which gives us 0, divided by 0 squared, again 0. So yes, we are in the case of this indeterminate form of 0 over 0, which tells me I've encountered a hurdle in trying to compute this limit by simply evaluating. So what we're going to try to do in this scenario is produce some sort of cancellation. We're going to have to try to simplify our fraction and get rid of the source of the 0 over 0. However, right now, there is nothing I can do algebraically because I have a root in the numerator. So the goal now is going to be to get rid of that root, and I can get rid of roots by the operation of squaring. So I'm going to take advantage of the formula in algebra, namely the a squared minus b squared formula, which gives me a minus b multiplied with a plus b. So what we're going to do in the following is multiply our numerator by the so-called conjugate. Namely, in order to take advantage of the formula a minus b times a plus b gives me a squared minus b squared, if I have the operation of minus in my given expression, I'm going to multiply by the same expression only with plus in between the two terms. So now I have a minus b multiplied with a plus b. More so, since I just changed my expression, right, this equal sign over here is no longer true because I changed the right hand side. In order to prevent that and still have the equal sign hold, I also have to divide by the same quantity, namely the square root of x squared plus 1 plus 1. Now, because I have multiplied and divided by the same quantity, this expression really simplifies to 1, and since multiplication by 1 does not change my expression, I still have that my equal sign holds. So now let's see why this helped. Well, as I said before, if I look in the numerator here, this is a minus b, where b is 1 and a is that square root, and now I've multiplied it by a, which is the square root, plus b. So when I have a minus b times a plus b, what I get is that I have a squared, so in my case the square root of x squared plus 1, which was a, is being squared, minus b squared, so 1 squared. So you notice that by multiplying by the conjugate, I was able to use this formula, and now the square and the square root cancel. However, I haven't gotten rid of that root. All I've done is basically move it from the numerator to the denominator because I have this leftover root now in the denominator. Yet that's not going to be a problem for us because the simplification we're after is going to still happen. So let's write down first what appears in the numerator. Since the square root and the square cancel, I have x squared plus 1 and then the minus 1, and now divided by the same quantity in the denominator. As I said before, we will be producing some cancellation. So now that I've gotten rid of the 1 and the negative 1, I can also simplify the x squared in the numerator and the denominator. So let's cancel these two out as well. And now finally I have the limit as x approaches 0 of the square root of x squared plus 1 and then the plus 1. And we notice now that at this stage, when I cancel the x squared over the x squared, that was the source of the 0 over 0, and I've gotten rid of it. So now if I try to evaluate, there is no more hurdle. I can simply compute this limit by evaluating. So I get 1 over the square root of 1 plus 1, which just gives me 1 over 2. So again, the idea underlying this particular technique involving roots and the 0 over 0 indeterminate form is to multiply and divide by the conjugate, because this enables me to use the formula a squared minus b squared and get rid of the root in the numerator. What do I mean by get rid of it? In essence, we're moving it in the denominator, but this squaring here enabled me to simplify my numerator and in essence to cancel the source of the 0 over 0. Our final technique involves trigonometric limit and the indeterminate form of 0 over 0. In the case of these limits, we're going to use this really important limit, namely the limit as x approaches 0 of sine of x over x equals to 1. And we can see this from the graph of the sine of x over x graph, namely the function is not defined at x equals to 0 because I have x in the denominator, and the function has kind of a bell-shaped curve near 0. It approaches the height of 1. It is important to notice that at no point does the function attain the height of 1. It is, however, in the limit that the function approaches the value of 1. So sine of x over x is not equal to 1. It is the limit of sine of x over x at 0 that equals to 1. So now let's look at some examples. Let's say that I have the limit as x approaches 0 of sine of 3x over 2x. So when I try to evaluate at 0, I get sine of 0, and then 2 times 0 gives me 0. So yes, I have a trigonometric limit, and I am in the case of 0 over 0. So the way we're going to try to overcome this hurdle is to try to take advantage of this important limit. Namely, we're going to try to match the input in my sine with the denominator. It's important to note that that 3 cannot be pulled out of my sine. That is not an allowed operation. Sine is not a linear function. So what we're going to do instead, as I said, is try to match the input of the sine, this 3x, with my denominator. So let's first clean up our expression. Let's pull this 1/2 in front of the fraction and just leave the x there by itself. This is going to enable me to match the input in the sine with the denominator. So in essence, over here, what I would like to have is a 3x instead of just x. So how can I do that? How can I make an x into just 3x? Well, of course, we can simply put a 3 in front of the x, right? I'm multiplying the x in the denominator by a 3. However, now this equal sign is no longer holding. Namely, I've changed my right-hand side by dividing it by 3. So in order to now ensure that the equal sign still holds, I'm also going to be multiplying my expression by 3, because the 3 in the numerator and the denominator canceled out into 1, so I have that the equal sign still holds. So now we notice that the input of the sine, namely 3x, is now matched with the denominator. So we, in essence, have that this formula is going to apply, namely sine of the same input over the same input is going to go in the limit to 1, provided the input goes to 0. And as x goes to 0, 3x goes to 0, so we're okay with that. So what we obtain here is that this limit of sine of 3x over 3x is 1. And finally, what we're left with is the two constants, namely the 1/2 and the 3, which we can, of course, pull in front of the limit or just copy them. And we're left with the final answer of 3/2. So again, the main idea in computing these limits is to match the input of your sine with your denominator, and then you can actually say that the limit of that expression, provided your input also goes to 0 as x goes to 0, is 1. So now let's look at one more example. Let's say we have the limit as x approaches 0 of sine squared of x squared divided by x to the 4th. So again, when I try to evaluate this function at 0, I get sine of 0 squared, which is 0. So sine squared of 0 is just 0 over 0 to the 4th, so we have 0. So again, I'm trying to somehow take advantage of that limit. So in the numerator, I notice that in essence I have two signs multiply with each other. So let's write them separately, because this might help me see how to solve my problem. Namely, I have sine of x squared multiply with sine of x squared. Now what I'm going to do is create two limits where I match the numerator with the denominator. Namely, I will have one for sine of x squared and one for the second sine of x squared. Now what would I need in the denominator to match these up? Namely, I need the x squared, the input, and another x squared here. And what do you know? That's exactly what I obtain when I multiply x squared by x squared. I get x to the fourth. So in essence, I've split that x to the fourth into two x squares, and now I have these two separate quotients, each of which is set up exactly so that in the limit it turns out into 1. So the limit of sine of x squared over x squared is 1, because as x goes to 0, x squared goes to 0, and the same is true for the second limit. So 1 times 1 equals to 1.